Here we want to use L'Hopital's rule to explore the number e, also known as Euler's number in some circles. Of course, e is very cherished and beloved in calculus. In fact, you can see again and again how calculus very naturally kind of bends around e and natural log. For instance, we had the example that the derivative of e to the x is itself e to the x again. Right? It's the only number that has that property. So there's a lot of very neat things about calculus and e and natural log. In math, we're always looking for ways to define e, because otherwise, how do we say what it is? Right? With pi, we can very easily say it's the ratio of the circumference to the diameter of a circle. But with e, we can't say that, right? What is e? And maybe you want to say, well, it's 2.7. All right, so e, well, great, approximately equals 2.71828182845, etc. 90, dot, 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 dot. It keeps going. But I'd have to keep talking and writing digits for eternity to actually say what e was. So that's not a good approach. What I'm claiming here is that this limit, the limit as x goes to 0 of the quantity 1 plus x, all to the 1 over x, equals e. And if that's the case, we can use that as a definition of e. So we'll say is the definition. We can sometimes write this 3 lines here to say that e is defined as this quantity. And then we have a nice way of saying what e is. It's not quite as concise as saying it's the ratio of the circumference to the diameter of a circle like we can for pi, but we can say, hey, it is this limit here. So let's see if we can get e out of this limit. Okay, well, the first thing we do is to try to evaluate the limit flat out. If we put in 0 for x, we get 1 to the 1 over 0, which is infinity. So it is indeterminate of the form 1 to the infinity. But recall that L'Hopital's rule only works for limits of the form, or that evaluate to the form 0 over 0 or infinity over infinity. We have 1 to the infinity. But once we get it to the form 0 over 0 or infinity over infinity, we simply take the derivative of the top, derivative of the bottom, and divide them. So let's get it to that form. The key here is to take the natural log of both sides. So I'm going to write this as y equals 1 plus x to the 1 over x, and take the natural log of both sides. What that does, of course, is get this exponent down to the front. So we now have natural log y equals, the 1 over x comes down, so we have 1 over x, natural log of 1 plus x. Okay, and now we're ready to take the limit of both sides. So we'll now take the limit as x goes to 0 of both sides. Limit as x goes to 0. So we took the natural log up front, which means we're going to pay that back by taking both sides base e later on. Okay, as tempting as it is to start taking derivatives of everything, hold off. Let's make sure we're of the correct form. That's one of the biggest mistakes I see with L'Hopital's rule, is people take derivatives before they're in the correct form of 0 over 0 or infinity over infinity. If we evaluate this limit now, we get 1 over 0, which is infinity, times natural log of 1, which is 0. So we're still not quite there. We are of the form infinity times 0. Well, we can simply rearrange this thing. It's a nice step to do, but again, I'm always shocked at how many people skip this step and just completely train wreck these kinds of calculations. Look, we can rewrite this as natural log 1 plus x all over x, and now when we evaluate it, we very quickly get 0 over 0. Check. Still indeterminate, but at least now we're in the form that we can use L'Hopital's rule. Okay, L'Hopital's rule tells us then to take the derivative of the top and the derivative of the bottom. So natural log 1 plus x becomes 1 over 1 plus x. There's no chain rule there to worry about. And then, of course, the derivative of x is 1, so that's all over 1. And we can evaluate this limit now quite easily to get simply 1. But I thought we were supposed to get e, and here we got 1. Well, remember that since we took the natural log up front, we need to take both sides base e at the end to undo that, essentially. So the correct answer here is e to the 1, which is e. Let's be a little more technical about that. We have the limit as x goes to 0 of, this is 0 there, of natural log y equals 1. I'll take both of these, base e. Because e is continuous, it can move inside the limit. So we get the limit as x goes to 0 of e to the natural log y. Well, that's simply y, because e and natural log are inverses, they undo each other, equals, on the right hand side we have e to the 1, which is e, which is the result we were hoping for. We can then go so far as to say e is defined as the limit as x goes to 0 of the quantity 1 plus x to the 1 over x. And this approach is essentially how e was discovered in the first place, right? They were looking at interest rates, and they weren't using the word limit because that came later, but they were saying, okay, they were looking at compounding, how many times you could compound interest in a year. So we had something like this, 1 plus 1 over x, all to the x. Or at least for interest, you may have seen this as n. N goes to infinity, 1 plus 1 over n to the n t, but then we let t be 1 year. So they were essentially looking at this quantity for interest and discovered e that way. And notice that these are equivalent formulations, just slightly different. So though it seems like something brand new that we just got in calculus, is actually a very old, in fact, the original way of studying e. One last thing, it may seem like we're doing some circular reasoning here because we're essentially using e, inherent in natural log, to somehow define what e is. But we'd have to know what e is to even take the natural log. Well, we already defined e to be the unique number such that when you take that number to the x, so in this case e to the x, and you take the derivative at x equals 0, it has a slope of 1. So let's use that definition of e to get around justifying using this natural log, and then we arrive at a new definition of e. And then in Calc 2, once you study sequences and series, you get an even better definition of e using an infinite sum. So there's something to look forward to. But you can see this number e runs deep all through calculus.